Okay, so there's two questions that I wanted to talk about here, and I realized that I probably should have pasted the screenshots in before I cut the last video off, but so this will just be like a separate video. Um, but the first one is saying that, you have this enzyme and it's got a Vmax value of 540 nanomole per second, and he's given you the Vmax over Km as well. And so you're asked to calculate the value of alpha. And so a lot of people in Action Center were asking me, like, do I need to know what type of inhibition it is from the information that he's given me? Or, just things like that. So the answer is you don't, because he's told you to calculate the value of alpha. You can just automatically assume that, like, you don't care what type of inhibition it is, even if it's non-competitive or mixed or whatever, and it's got, like, an alpha prime term. He's only asked you to calculate alpha. So you can just treat it as if you were calculating for competitive inhibition. And so the thing to recognize here is that in competitive inhibition, the slope gets modified. And he's given you slope values. He's given you the reciprocal of slope values because he gave you Km over Vmax, and the slope is going to be Km over Vmax. He's given you Vmax over Km. So you just have to flip the number. And so how this works is the true slope is going to be modified by some factor, alpha, to give you the observed slope. And so we can write that as alpha times Km over Vmax. This is the true slope. That's going to give us Km over Vmax that we observe, or apparent. And so if we actually plug in the numbers here, we get alpha is equal to 1 over 0.48. Oh, that's not an equal sign, that's a times. That's going to be equal to 1 over 0.08. And so we actually do the math out, and we get alpha is equal to 6, and that's our answer there. And so in the next question, he'll ask you to do the same thing, but you'll calculate alpha prime. And so alpha prime will also be 6, and this is something that I forgot to mention before when I was talking about non-competitive inhibition. But the type of non-competitive inhibition where the x-intercepts will be the same on the graph, that's called pure non-competitive inhibition, and that only happens when alpha and alpha prime equal each other. And I think that's pretty rare. Now, the second thing I wanted to go over was something that a lot of you guys had asked me about before. And it's this question, and I understand that one of the things that's so hard about this is just the fact that he's given you so much text to deal with, and so sifting through that to find what you actually need to care about. And so when I go through these, I'm thinking about, like, okay, he's given us a y-intercept value and an x-intercept value. The one that I care about is the x-intercept value, actually, because I know that I can express my x-intercept in terms of Km, and he's told me that this inhibition is competitive. And so competitive inhibitors are always going to affect Km. So I know that I can use that fact to sort of make this problem easier on myself. So I have an x-intercept here, and I have another one here. Now, he's also given me the concentration of the inhibitor, and he wants to find the Ki. Now, the way that we can do this is that if you'll remember from how competitive inhibition works, I showed you that the x-intercept of a competitively inhibited reaction is going to be -1 over alpha times Km. And so the same logic that we applied to this question, we can apply here as well. So what we can say is that the x-intercept, that's going to be equal to -1 over Km normally. So what happens in this case is that we've got some alpha times -1 over km. This is the true value. That's going to give us -1 over km that we observe, the apparent value. And so if we plug in those numbers, the 20 and the -6.67, we'll end up with the fact that alpha is going to be equal to 3. I think you get like 2.99 or something that you can round to 3 if you actually do that calculation out. And the important thing to remember here is that he wants you to find the Ki. And so the way that you can do that is you have this equation that alpha is going to be equal to 1 plus the inhibitor concentration over Ki. And he's given you the inhibitor concentration. It's 84 nanomolar. And so you can manipulate this equation. You can say that Ki is going to be equal to the inhibitor concentration over alpha minus 1. So we can say that 84 is going to be equal to 3 minus 1. That's going to give you 42 nanomolar.